Hey, what's up? It's your old pal, Mr. Cook. We just got through these two interval of convergence problems. Took a little bit of time, so I thought I'd stop that video when I reached like the 78-minute mark or whatever that was at. Okay, I think I could probably get through the next four in one video. Yeah, I think so. I think we get through the next one. Okay. Yeah, so we'll just do one more video for this one. So 17, if we've got this function, we want to find the derivative of the function and then also the antiderivative of the function. This can look really intimidating. I get it, but it's actually like super easy. All you got to do is just think for a second. It's like, okay, if this represents the function, then when I take the derivative of it, I'm taking it with respect to a variable, and the variable is going to be x. So think back to your time when you were doing implicit differentiation. When you were trained to take the derivative with respect to x, you only took the derivative with respect to x. When you were trying to take it with respect to y, you only took the derivative with respect to y. So in this case, we only care about the x value. We can think of all the n's and the sigmas and all this stuff as just like, it's just another number, okay? So when it asks you to take the derivative, just look at the function with the x on it. That's it. So it's just this. That's what you take the derivative of. Just that. X to the 2n. All the other stuff just gives you, like all of this stuff right here, all of it, it just gives you a coefficient. That's it. And what do you do with coefficients? Like if I had 3x to the fifth and I took the derivative of it, what would you do? Well, the 3 just kind of goes through, right? It just stays on there. It's a constant multiplier. And then we take the, we use the power rule on the x to the fifth. So the, 5 goes out front. So you have 5, and then x, and then 5 minus 1, 4. And there's your derivative, right? Power rule. Well, you just use power rule on these power series. No joke. So if I want to take the derivative of this function, I leave all the other stuff alone. N equals 1 to infinity, and then 2n plus 1 in the denominator. That's all just, we think of that as just the coefficient, like that 3 that I just had in that previous example. Then I need to multiply that by the part that I really need, the derivative of the x function, the function that has to do with x to the power 2n. And that's just another power. So we use power rule. Just bring the exponent power out front, so 2n, and then multiply that by x to the power of, the exponent power minus 1, so 2n minus 1. This is the derivative. I'm not kidding. That's all you have to do. So if I want to take the antiderivative of the same function, f of x, can you take a wild guess what I'm taking the derivative of? I don't care about any of the other stuff, only the x to the 2n. That's it. Because even if I had to take the antiderivative of, let's use the same one, 3x to the fifth, right? dx. That 3 just sort of like went forward, okay? Like a 3 right there, okay? So you have 3 times the antiderivative of x to the fifth. And then we would use the power rule for this one. We'd add 1 to the exponent power. Then we divide by that number. There you go. And you can simplify it any way you want. And then after you take this indefinite integral, what's the last step? Do you guys remember? You got to add c onto the end of it, right? A constant. Because if you took the derivative of this, hence get back to the original function, that constant, its derivative would just be 0. So it just disappears. And that's the same steps that we're going to do for this thing, for the antiderivative of f of x. So all of this stuff here, all of that, those are just coefficients. So again, when I take the antiderivative, the coefficient stuff stays the same. N equals 1 to infinity over a 2n plus 1. That's all the coefficient. Think of it as the coefficient. Now let's just take the antiderivative of x to the 2n. So the way that we did that with the power rule is that we took x to the 2n, and then we just add 1 to the exponent. And then what do? We divide by that number. So we're going to divide by another 2n plus 1. There we go. There's the antiderivative, but not quite. We're not quite done, right? What do we forget? Plus c. Now, here is something that can be a little tricky, all right? I need you to pay close attention. You've got to add the constant over here, okay? Plus c goes in the front. Here's why. If you accidentally put plus c over here, then it's implied that you're taking this whole entire summation like this. So you're adding in c infinitely many times. You don't want to do that. You only want to add it in once, because when you take the derivative, just a constant, that's the part that goes away. So we add c in the front, right over there, okay? There you go. That's the derivative and the antiderivative. And that's all the work that you need to do. Yeah, I know I can square this, okay? I'm not gonna, because I can just leave it like that, and that's the answer. Okay, so there's number 17. Sorry, I didn't mean to get combative there, but I just had like a Mountain Dew, so like maybe I'm a little bit over caffeinated right now. I don't know. Anyways, now number 18. So it says if, oh, that's some weird notation. If that thing, okay, then find the Lagrange error. Oh, Lagrange error, okay, of the upper bound if a third degree Taylor polynomial centered at x equals 7 is used to approximate f of 7.3, and then assume the series converges at x equals 7.3. All right, you know what? When I see that Lagrange error, I should know this. Lagrange error upper bound, there's like this formula that goes along with it, and here's how it goes. Ready? The upper bound for error it's always less than or equal to the absolute value of this thing, okay? And here's how you construct it. Here's how you put together the equation. You use that Taylor polynomial pattern, Fn of c over n factorial x minus c to the power of n. And you just do two little tiny changes, okay? Two changes. Every n that you see on there, change to an n plus 1, okay? Every one of them. And then this little c that's, in that derivative function, you change it to a z. There you go. This is the Lagrange error for the upper bound of some Taylor polynomial. And when we see this, we should really be thinking about the alternating series test error, okay? Because what happened with that one is that the amount of error that you get is always less than the next neglected term. Well, this is the next neglected Taylor term in a polynomial, okay? And then on top of that, we need to find this value, z. So it's not enough to just say that it's like less than the next Taylor term, because Taylor terms have a lot of moving parts to them. It's not just like plug into a series and you get an answer. The Taylor term has like a derivative attached to it. So to make sure that you have an upper bound, you want to find this value z, and z is like the biggest possible, it's the x value that leads to the biggest possible derivative over some interval. And that interval is going to go from x to c, okay? And we'll show you like what to do with all that stuff. It's actually like pretty easy, believe it or not, when you work through the problem. Okay, so we need to know this, all right? This is what we use, this formula, when we see Lagrange error of an upper bound of a Taylor polynomial, okay? So that's the first step. That's step one. This is the formula that you're going to use. The second step that I like to do is just start plugging stuff in. So stuff that I know. Like, for example, if it's the Lagrange error for a degree 3 Taylor polynomial, it's implied that if it's a third degree Taylor polynomial, that n is going to be equal to 3. So guess what? N is 3. So if I have an n for 3 there, 3 plus 1 is 4. That becomes a 4. That becomes a 4. And yeah, sure enough, that becomes a 4 too. What does this part mean? Well, this means that I need the fourth derivative. I know the fourth derivative. That's this stuff over here. So that mystery information they gave us at the very beginning, I didn't know what it meant necessarily. Let's look a little bit further into it. What it's saying is that the fourth derivative, okay, for any x value that you use, it doesn't matter what the x value is, if you take its magnitude or like the absolute value of it, it's always going to be less than or equal to 4. So in other words, 4 is like a ceiling on it, okay? Like like the derivative can't get beyond that value. It's like the biggest possible value that you get for the derivative for any x. So I'm going to store that information away. So this tells me that the following information, it says that the biggest value that f4 of x, f4 of x can be is 4. That's the biggest that it could possibly get, the absolute value of that, okay? I'm going to remember that. All right, and I'm going to keep plugging stuff in. Like C is the center. Can you see where it says centered? Yeah, centered at x equals 7. So that means that C is equal to 7 in this case. There we go. And then x, I'm always going to find from where it's approximating around. If it's approximating around like this function right here, f of 7.3, 7.3 is the x value. Okay, so I'm going to put a 7.3 right there. And you'll see this is consistent for number 19 as well. And I believe number 20. Yeah, number 20 as well. Okay, so there we go. Now let me simplify this a little bit. So 7.3 minus 7, that's just 0.3. Oh, actually, I shouldn't have erased that yet. So 7.3 minus 7. I'm going to leave that up there for a second. So usually what happens at this point is then we'd be given the fourth derivative, or we can solve for the fourth derivative, and we would graph it out. And we'd look over this interval. So starting at 7 and going all the way up to 7.3. And maybe the graph looks like this. It's like something funky like this or something, right? What we would do is we would only look at like just the interval of interest from X to C. So from here all the way over to like here, I guess. And we just look at this graph. And this thing right here would be the biggest possible Y value that you get there. So it looks like it's like right over here. Whatever that Y value is right there, that's what I would plug in. That number would go in, in place of this thing, okay? But I don't have the function to graph out. I don't even have like the first step of that. I just have this stupid inequality. But the inequality ends up telling you everything that you need to know. You don't need the graph. You don't need the function. You know that the biggest value that this can possibly be, in other words, what we're looking for with this stuff over here, it's 4. So that's what I'm going to replace it with. I'm just going to replace it with a 4. So I can just get rid of all this stuff over here and just replace it with a 4. There we go. Now look at this. It's all just a bunch of numbers. So if I just calculate it, it's going to give me the upper bound for my error. So the upper bound for the error is going to be less than or equal to the absolute value of 4 over 4 factorial times 7.3 minus 7 is 0.3 raised to the 4th power. So whatever that number is, and it's going to be positive no matter what, that is the upper bound for the error, okay? And I should really say that this is error, and this ends up being, this is the upper bound for the error. And you can just leave it like that. Like, you don't have to simplify it or anything. That's good enough for us. Okay, there we go. There's our number. When I put step 1, I was like, oh, what's step 2? Doesn't matter. Okay, whatever. Next up, number 19. 19 is very similar, but they give us the function for the 6th derivative for some weird reason. Wonder if we're going to use it. So the Lagrange error for the upper bound, I know exactly what to do for that. I'm not even going to read the rest of this because I know that the error is going to be less than or equal to the absolute value of my Taylor term. But wherever I see an n, I'm going to replace that with an n plus 1. And then I'm going to replace the c with a z. There you go. There's my Taylor, the Lagrange error bound formula. Okay, there you go. That's it. And this is the upper bound that I'm going to be looking for. Okay, just to kind of like put it all out there. All right, so let's start plugging in some of the stuff because the rest of it's just formatted the same way. It says that I'm looking for the error of a 5th degree Taylor polynomial. 5th degree tells me the n value, 5. So 5 plus 1 is going to be 6. So all these are just going to turn into 6s. 6, 6, another little 6 in here. There we go. And then x minus c. Well, c is where it's centered around. Let's see, centered at x equals 3. So that's going to become a 3. And then x, that's the number that's inside the function. So like the number that I'm kind of approximating, so 3.1. The last thing I need to get is z. Well, z can be found at, it's the maximum of this. So this whole entire term right here, the whole entire thing is just going to be the maximum number that I get over the interval from 3 to 3.1. So I'd graph this out. So let's see what it looks like on my calculator. All right, let's see here. 40 sine of x. Okay, there we go. And then, sine is, it goes up and down, right? And then if it has a 40 in front of it, that's the amplitude. So it's at least going to go up to 40. So I'm going to change my window. Let's see here. So I'm going to look from, here's my interval, right? It's going to be 3.1 to 3. So I want to maybe go from like 2.5 to like 4 maybe. I'll go up by 0.1. Excuse me. My y minimum, well, sine goes up and down by 40, so it'll go all the way down to negative 40. So I'll do negative 45 up to 45, and then I'll go up and down by 5s. So that should give me the sine graph that I need. There we go. All right, so 3. Well, it looks like it's just decreasing the entire time, right? So where did I start at? I started at 2.5, right? Okay. So let's see here, 2.6, 2.7, 2.8, 2.9, 3 would be like right there. And then 3.1 would be like right there. So it looks like it's just decreasing the whole way. So where's the maximum going to be? The maximum is going to happen exactly at 3, right? Because that's the biggest that this graph goes to, because everything after that's like negative, it looks like. So at 3 is going to be the biggest possible value. So that's what I'm going to do. My z value is equal to 3. And that's the last thing I got to plug in 3. All right, so here we go. So there you go. You use your graph. You find out where the maximum is. Easy stuff. And then we just start plugging the stuff in. So this is going to be, let's see, your absolute value of f6 of 3. So in other words, we're going to plug in 3 in here. So 40 times the sine of 3 over 6 factorial. And then times 3.1 minus 3 is going to be 0.1 to the 6th power. And then, yeah, this is calculator time. I don't know if that's going to be negative or positive, so I'll leave the absolute value on that. But that's going to be my upper bound. There you go. So there's your answer right there. There's my upper bound. All right. We got one more. And it's the same type of problem. So find the Lagrange error upper bound. Oh, man. I already know that stuff, don't I? If a 4th degree Taylor polynomial approximating this function, okay, so 4th degree Taylor polynomial, that means that n is equal to 4. Now let me write down my Lagrange formula. The error is less than or equal to this like Taylor pattern, right? Fn of c over n factorial x minus c to the power of n. But I replace all the n's with n plus 1. And then I replace that little c in there with a z. That means maximum, right? Okay, and then, yeah, n equals 4. So that means if n is equal to 4, then these are all 5s. There you go. And then let's see. So x is 3.1. And then it's centered at 3 again. All right, so where's the challenge in this? It looks pretty easy so far. Wait, where's my derivative formula? Look at that. In 19, I had a derivative formula. And same with 18, I had like an idea of the derivative. They didn't give anything like that to us in 20. Well, that's okay, because, you know, this is the function that we're dealing with. So if you're not given the derivative formula, you know, find the derivative, right? Of course. Okay, so we got to find the 5th derivative here. If f of x is equal to e to the x, well, wait a minute, it's e to the x. What's the 5th derivative going to be? Yeah, it's just going to be e to the x, right? Because the first derivative is e to the x. The second derivative is e to the x. The third derivative is going to be e to the x. And so on, right? We're just going to end up with, you know, a 5th derivative equal to e to the x. And then if it's centered at 3, that's what we're going to plug in. Oh, wait, actually, sorry. Hold on. We might not be plugging in 3. Let's see what we need. All right, so this is the 5th derivative right here. Then what we would do now is graph out the functions just like we did with the sine. So we have e to the x, that's our 5th derivative of x. And e to the x looks like this. I don't even have to use my calculator for that. It looks like this. So if it starts at 3 and then goes all the way up to 3.1, and that means that our maximum is going to occur right over there. That's our z value. Z is 3.1. So I'll put in 3.1 right there. Okay, so now let's calculate this out. So this is going to be equal to absolute value of, and then remember the 5th derivative is e to the x. So if I plug in 3.1, I get e to the 3.1 over 5 factorial. And then 3.1 minus 3 is 0.1 raised to the 5th power. So whatever that number is, that's going to be my upper bound. There we go. You just leave it like that if you want. I'm sure that's good enough. Okay, so that's the whole worksheet, or review worksheet or whatever. So I hope you found this last video helpful. I know that this is an intimidating topic, the Lagrange error. It's tough if you don't quite, if you aren't comfortable with inequalities or all that notation and stuff. But hopefully I've shown you just, the bare bones stuff that you need to focus on, to get this problem done successfully and get the answer, the upper bound on the error. If you didn't really find it fun or helpful, right? Obviously, just reach out to your calc teacher, get some help from them. They'll give you more examples, maybe reinterpret it or graph it out so you can see what's going on visually. Maybe that can help you out. I just want to show you the easiest way to get this stuff done, get it done accurately. Anyways, okay, so like I said, I hope you found it helpful. If you didn't, go find your math teacher. I'm Mr. Cook. I'm always here to help you out. If you need help in the morning or after school or even during lunch, if you just shoot me an email, I'll try to, accommodate. Get some help. Okay, this is tough stuff. If you need it, go find it. Go find the help. Yeah, and that's it. So hey, good luck on your test, and see you in the next video. Bye-bye.